Hi there, and welcome to a Scratch tutorial. In this video, we will be programming a clone-based 3D engine. If you've spent much time on the Scratch website, you may have played a 3D game and wondered how exactly someone managed to code a 3D game in the 2D coding language of Scratch. There are many 3D engines on Scratch, and most of them use the same three components: the 3D projection script, the rotation matrix, and the sorting algorithm. We'll start with the projection script. The job of the projection script is to take a set of 3D coordinates and project them onto the screen to create the illusion of 3D. We'll build it here in a custom block. Before we can finish and test it, we need to create some variables: camera X, camera Y, and camera Z, which will be for all sprites, and object X, object Y, and object Z, which will be for this sprite only. The camera X, Y, and Z variables represent the coordinates of the camera, and the object X, Y, and Z variables represent the coordinates of the object that we will be projecting onto the screen. Now we need one more variable: distance to screen, which will be for all sprites. For now, we'll set this to 300. This represents the distance from the camera to the screen on which we will be projecting the objects. To understand why we need this, let's look at where we get the mathematical expressions that are used in this script. Here's an object that I have projected onto the screen. If we pull the camera back, we can see where the object exists in 3D space behind the screen. Now, if we pass a line from the object to the camera, it will pass through the screen at the point at which we want to project the object. If we move the camera back to its original position, we can see that the point on the screen is exactly where the object is projected. The only question is, how do we find this point mathematically? Luckily, we can find it with some simple triangle geometry. We can set up two right triangles, one between the camera and the screen, and one between the camera and the object. Let's call the legs of the bigger triangle A1 and B1, and the legs of the smaller triangle A2 and B2. Just to clarify, A1 extends all the way to the camera. Because these triangles are similar, that is to say their angles are equivalent, the ratios of their corresponding sides are also equivalent, so we can set up the equation A2 divided by A1 equals B2 divided by B1. Since we are trying to find the y position of the point on the screen, we'll solve this equation for B2, which gives us B1 times A2 divided by A1 equals B2. Next, we'll swap out A1, B1, A2, and B2 for object Z, object Y, distance to screen, and point Y. This, if you remember, is the mathematical expression used in the code. Plugging in our given values, object Y is 200, distance to screen is 300, and object Z is 700. This equals a number that rounds to 86, which is the Y point that we are looking for. Thus, we can see that the math in our code works. Before testing the projection script, we'll take the opportunity to add some basic camera movement. We'll create a new sprite for this. This forever loop will update the camera position, which is controlled by the arrow keys. Next, we'll add one more block: broadcast frame. In the other sprite, we'll put the object scripts under a when I receive frame block. That way, all objects will update every time the camera position is updated. To make it easier to add objects to the world, let's make a custom block. Now, let's use it to add a bunch of objects to the world. Now we can see that the projection script works. However, there is one more thing we have to add to this script. You might have noticed that even if the object is behind the screen, it is still visible on the screen. We can't have that. To fix this, we'll just add a simple if-else block to hide the sprite if it is behind the camera. And there we are! The 3D projection script is complete. Now, you may have noticed that currently we can only face one direction in our 3D world. The next part of our engine, the rotation matrix, solves this problem. Basically, a rotation matrix rotates one point around another point. In this way, it can rotate the object coordinates around the camera coordinates, producing a new set of rotated coordinates that the projection script can use. The script here is relatively short and simple, and we will again be building it in a custom block. First, we need three new variables: camera direction, which will be for all sprites, and rotated X and rotated Z, which will be for this sprite only. Now we can build the script. To add the new script to our forever loop, we need to change a few things. Now, the left and right arrow keys will turn the camera, and the up and down arrow keys will move the camera forward and backward. Finally, we'll test the script. As you can see, the camera rotates and we have a 3D world. However, there is still one problem. Sometimes an object that is farther away will appear on top of a nearer object. To fix this, we need a sorting algorithm. From quicksort to bogosort, there are many sorting algorithms that we could use, but the most efficient one for our purposes also happens to be the simplest: insertion sort. This is because, in clone-based engines, the objects tend to already be almost sorted. Just like the other parts of this engine, we'll build this part in a custom block. Here, make sure to check Run Without Screen Refresh. We have to do this anytime we have a loop in a custom block that we want to execute within a single frame. Before we write the rest of the code, however, we need a list and a variable. We'll call the list distances, since that is what we're sorting, and this list will be for all sprites. The new variable will be called I, for this sprite only, and will serve as a counter as we work through the list. Now we can build the script. When scripts are run in multiple clones on Scratch, they are executed in layer order. That is to say, the clone that is on top will execute its script first, and the clone on the bottom will execute its script last. The sorting algorithm figures out where the clone should be layered in relation to the other clones, and then it moves the clone to the correct position. Let's run the program to make sure everything is working. And there we have it, a working clone-based 3D engine on Scratch. Thanks for watching! There's still a lot we can add to this engine. Vertical looking, collision detection, and object movement are all topics I'd like to cover in this series. If you enjoyed this video, please like and subscribe, and I hope to see you in part 2.